Whoops. Now we'll get started. All right. So today we're going to finish up our discussion on binary search trees, and then I'll assign a lab which isn't due till after spring break. Yeah, I'm that guy.
Wait, it's due after spring break or like during spring break?
After. Oh, during? Oh, man.
No.
No, I don't have time.
No. I'm going to be in Hawaii.
I already wrote the lab and I already committed to GitHub, so it's already too late.
Good.
Okay, good. Yeah.
Good.
I'd like to introduce you to a certain concept, Dr. West. There's an idea called mercy. It's something that's also talked about in the Bible too. So maybe you might want to consider it a legit thing.
Wasn't there also spare the rod, spoil the child? All right. So back to what we're learning. In the binary tree, in each node. Okay, so a binary search tree. Just remember, at each node, what was it? Larger data is to the left of the child. What? No, it's backwards.
Oh, you know.
Wow, look at the instructions. Larger data is left of the child.
Nice. That is actually reversed.
Yeah, that's beautiful.
That picture even proves it.
Yeah.
And, you know, we
Trust the picture, aka you're at this child. Everything to the right of the node is larger. Everything to the left is smaller. All right, there we go. So we already defined a binary search tree. The picture actually makes more sense. We went ahead and said a binary search tree can be empty. You can search for an item, insert or delete, find the height, find the number of nodes and leaves in the tree. Ooh, traverse the tree and copy the tree. So we talked about searching. How do we search in a binary search tree?
By searching.
By searching. What type of function did we use? Just trying to get everyone back on track. Recursive, right. So let's jump over and look at the code that we used. So, for example, good morning.
Morning.
Story time.
So I was grabbing breakfast on my way here, and then all of a sudden I was pouring pineapple juice into this cup. I was walking a few steps, and all I see is this yellow sponge. Little did I realize I killed SpongeBob.
Oh,
You killed SpongeBob?
does that mean the show is no longer
Yeah,
going
it
to air?
got canceled because I killed him, so now I have to deal with the IRS and with all his taxes too for some odd reason. Which reminds me, tax season's coming.
It's already here.
Yeah, it's already here.
Oh.
There's no need to remind me of sadness.
Yeah, I'm doing them next week. Well, yeah, all that money that I don't get back.
Anyways, back to in-order print. So we did it recursively, which was first take care of the base case, where if we want to print something out and it ends up being null, don't do it and just return. Don't do it. And then first we recurse down the left side because we're doing it in order. And once it goes all the way down the left side, can't find anything, then it's going to print the data and start recursing back. Once it prints the data, it needs to also go down the right. And of course, it'll recurse back up. Hopefully I'll remember this from my stack pictures that I drew.
Those really nice pictures.
Oh, good. I'm
A
glad.
lot better than what the slides provide.
Yeah, well, the slides help.
Better than boxes.
Huh?
I like circles better than boxes.
You must have been a special kid growing up. Did you write on circles of paper? I thought so. Okay. By the way, I'm just kidding for people online.
Sure you are.
Circles of paper. I'm just kidding.
Circles are important too.
Circles have feelings.
Circles. They're just not as pointed feelings.
Yeah, they're softer.
They're softer, more well-rounded.
What are we doing?
We're making jokes about circles.
All right.
Maybe they point to boxes.
Yeah.
We have problems.
You know it's bad when you just start joking about shapes. Oh my gosh, wait.
Welcome, Jonah. We're just not going to start today. It's going to be like 30 minutes and we'll finally get started. No, I think Jonah just interrupted you.
Sorry.
I need
You got to tell me what happened because SpongeBob apparently got killed this morning.
SpongeBob got killed this morning?
by Craig.
He murdered.
What?
Yeah, I called them.
I
You know
like
what
to
he
say
did?
that there's pineapple.
So sad.
He whipped out his sword and we just like.
Oh my god.
So, did you resurrect him, Jonah?
Huh?
You resurrected him?
I didn't resurrect him.
Oh.
Right?
Oh wow.
Wow. We have no love here.
Wait, I'm sorry.
Okay. All right, on to search.
Sorry.
So search steps. We start the root node. If no match, go down to the smaller on the right node. Was it root node? Oh wait, did we ever do search?
Nope.
We didn't.
I don't think so.
Was that part of your lab?
Nope.
I have no idea. I just looked at it last night, not gonna lie.
All right, let me make sure it's not part of your lab, so I don't accidentally
got
code
it.
something.
Dang it.
I think it is part of your
I
lab.
don't think so.
We got
I
put,
don't see it.
get height, in order. Oh, good. It's not part of your lab. Great. So we can do this in class.
Don't you wanna know?
So how do we search something? Well, we probably should draw a binary search tree on the board first.
Something went away.
And this time I'll use circles. Okay?
Oh.
Circles. Sorry. Someone give me a root node.
A what?
Come on, give me a number.
A.
A
That's
number.
a not number. Let's do 67.
All right. A. I'll translate. Lowercase or uppercase?
Aw,
Uppercase.
okay.
All right. So 65.
My number. I said 67.
You said A. Oh, 67. All right.
Yay.
Is that C?
That's my softball number.
Yes.
That's what I
69.
like.
69.
I had a total this week at work that came to 69.
Thank you for that update. My life is now better.
I had a good giggle, so.
Anyone else?
13.
13.
Okay, something out of the 60s.
My circles all of a sudden got, or just getting
Yeah,
smaller and
really
smaller.
tiny.
Which one?
2.
2.
56.
56.
72.
72.
23.
23.
63.
63.
Oh. 1.
1.
-1.
Negative 1.
Oh. Oh.
65.
We can have bacon.
Negative.
Where are you been?
Yes.
All right.
7.
Let's fill something out. Let's at least get 68 in here.
Oh.
And then you said
Whoa.
7?
Wait.
I said 7, yeah. Okay, never mind. I'm good.
Oh, wait. That was wrong. Oh, that was totally wrong.
Yeah.
I meant 66.
Yeah.
Now we'll go ahead and do
That's 68. I was really confused.
All right. And then we
Is
had
it-
what? 7?
Yes.
All right. Okay, hold on. I think this is already going to be too big for what we want, but that's
oh,
okay.
man. Sorry, the room is really loud. Usually
Actually,
comments are
It's
quiet.
balanced though, isn't it?
Not quite,
It's mono.
because this
It's not
has
balanced.
2 no children, and this one's
Oh.
over here. So if we somehow shimmied one in here and got rid of this guy on the level, on this level, it'd be balanced. Yeah, apparently shimmy is now the new word. Okay, there you go. People online, that's actually 56. There we go. Okay. So if we were trying to find 23, bless you. Excuse me. How would we go about looking for 23?
Pre-order.
Pre-order. So you'd want to traverse the entire binary search
No.
tree?
Well,
No.
you could cut it in half.
You just see if it's less than 65.
Okay.
So if it is, you go to the left. Is it less than or greater than 13? No, so you go to the right. Is it less than or greater than 56? Yes. It's less than, so you go to the left. And then you find 23.
Okay. So,
Da-da-da.
bum, 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 bum. All right. So you start at 65. Is 23 less than or greater than? It's less than, so we go over here. So greater than or less than 13, it's greater than, so we go to this 56. Is it less than or greater than? It's less than, and then boom, there's 23. All right.
Mm-hmm.
So how do you want to code this?
That's a good question. I don't know the answer to it.
This is one situation where the recursive and iterative are both simple. Why not both? All right. Right? Why not both? All right. Hold on a second. Let me make the size a little smaller, because
Oh, yeah, it's
otherwise it'll be huge and annoying.
really
And then mod 1000, that'll be fine. Oh, we just put in a bunch of numbers and ignore the rest. That sounds great. Oh. Oh, let's see if we can construct the tree from here. So what did we put in first? 65?
Yes.
And then what did we put in? 67?
Sure.
We'll probably put in 69.
Oh yeah, we did.
And
And we
then
did 13.
we're going to go ahead and put in 72 because that's okay. And then
No.
68. And then lastly
66.
66. All right, so that should form the tree that way. And then we're going to put in 13. And then
56.
56, sure.
63. And then
63.
you can't see the rest of the numbers.
63, 23. 23, 2, 1, -1, and 7. All right, let's see what that does. Should have made a makefile. Let's see, dash G, binary tree, BT, main. Hey, there's an in order printout. All right, so let me go and make a makefile of this. The makefile, all, tab, and then we'll just run it. There. Now if I just type make, it does it. All right. Okay. That looks great. All right, so we want to figure out how to do search. Now, really just contains is what we're doing, right? So we want to find out, does it actually contain something? So let's see, what do we got? We got public binary tree. Here's the public section. We'll scroll down to the bottom, or maybe right here, and we'll do bool contains. And we'll do int, actually we'll make it constant, int val. All right. So where do we start?
Top. The root.
The root. All right. So we need to do something with the root. What should we first do?
Well, first we need to check to see if the root is greater than
All right. So we need a temporary pointer.
yes.
All right. So we'll do. What should we call it?
Temp.
Temp.
What do we normally call it?
We do normally call it temp, but let's call it something a little more meaningful, like rover.
Fine.
And feelings too.
What has feelings?
Whatever we're doing.
Temp.
Not everything is. All right. So what we need to do? Figure out what about.
You would sit in my
See if it's
face.
greater than or less than. Hey, she's getting feisty.
We see if
I'm over here.
we see if root is what if I
Greater
mean.
than or less than.
Oh, if romer.m data, I think that's right, is less than val. Actually, shouldn't we first check if it is val?
Yes.
And if it is,
Just
return true. Okay.
It's so large.
Yeah, we're just going to return whether it contains it or not. Okay. Then what else do we do? It is a good question. I can
Then
tell.
we check to see if it's less than or greater than.
Rover.m. I should use this instead. And let me go fix it up here. So if rover's mdata is less than val, what do we need to do?
Then we need to go to the left.
All right, so we'll have rover equals rover m left. Okay. Else,
Then go to the right.
okay, rover equals rover m right. So we really want this to be a loop of some sort, right? And what's the loop testing?
We're trying to find val.
Right, we're trying to find val, but if the val never pops up, let's say we're over here and we go we're trying to find 24, and then there's nothing here. What's over here?
No.
Null. So we need to stop when we hit null. So let's go while rover does not equal null. That's all caps. Well, that's not what I want to do. Go. Let's go and space this out. Okay. And then if we don't find it, then return false. All right. Okay. Let me comment this. So rover will traverse down the binary search tree while we still have a node to evaluate. Return true if we have found the node. Otherwise, go left/right, depending on the value of val. All right, let's see if this works. So we have print, and then we can do cout. What's it going to be called? ib tree dot contains. Let's see if it contains 23 equals. All right, and of course we need to figure out if we actually compiled or typed everything correctly. Nope. That would be a note. So we were close. I forgot to do it. Are we really templating? Is this one templated? It is templated. Oh. Okay, so let's go back and template things. So it's not constant int, it's actually constant t. And the binary tree note is actually of the template t as well. So now let's make it. Yeah. Contains 23. No! Let's see if it contains, what's the other value? 20, just 24 in there?
No.
Let's see if it finds 20. Yep, it doesn't, it didn't find it. Oh no. Okay.
There's an actual problem with code itself.
Well, yeah. It didn't work.
Whoo!
The stupidity is strong with this one.
I was actually gonna say, man, you're working on your captaincy?
Yeah, I am.
You are? Okay. Whew. All right. So, what's wrong with this code? Everything. All right. Well, let's go ahead and do some printouts if no one can see it. Cout. We'll have %d. Actually, not %d. Arg. I'm so used to print it. Arg. Does that equal val?
That was a question.
Yeah, question equals.
No, you had a question. That was the way
yeah.
you said it.
He wrote a question sign and equal sign.
Hmm.
Making it seem like this question.
So it goes 65, 67, 69, 72. What does it look like it's doing? Bum, bum,
It's
bum.
going to the right instead of the left.
Ah, so actually, if the data is greater than val, we want to go to the left. Otherwise, we want to go to the right.
Are you doing that backwards?
Now, here we go. Hey, look, it contains 23, but it doesn't contain 24. All right, we'll get rid of this. Okay.
See, something that small.
Yep. All right, what's another number just to make sure it's working properly? How about -1? -1. And how about -100? All right, let's see if it does that. Good. Contains -1, but doesn't contain -100. Okay. Well, that's good. So everyone like this one?
Yes.
Yes. Okay. Why don't we write the recursive version? So the recursive version is going to have to be past, of course, the val, but it'll also be past the node that you're currently looking at. So binary tree node on t, pointer to node. So if we're doing this recursively, what's the base case?
That there's nothing
there's nothing that, yeah, so node points to null. Null. If node equals null, return false. I will need to spell false correctly.
Full cell.
All right. What's the next test? Here, I'll
The copy pasta test?
we'll copy.
Copy pasta.
Return true if we have found the node. So how do we test that? If. Yeah, but it's not rover this time. It's
Node.
all right. Node dash m data equals val. We'll return true. Otherwise, let's check. What do we check? Okay. Let me go ahead and just copy this. Good old copy pasta. Now we're greater than val, then we need to do contains.
It's node. And you have a space up there by that one. The if node space data.
You also need another closing parentheses as well.
Where?
Contains. We'll pass it val again, and what else are we passing? Node m left or right? Left. Otherwise, okay. All right. And actually, we should return those, since we're returning a Boolean. Return whatever goes down the left and whatever goes down the right. Okay. We win. Let's see if that actually works. So we'll just have regular contains, pass in val, and of course mroot. And we'll just say return that. And we'll just ignore the rest of it. No, this is C++. It doesn't care.
Does.
All right, there we go.
Hey, it did it right.
We did it right as well.
0, 1, 0.
Everyone able to follow me? Okay. Sure?
Yeah.
Yeah.
Was thinking.
All right.
1, 0, 1,
Lastly,
0.
because when you're looking at people write C++ code, you'll see them do this. Return contains, passing in val, and then we'll do node m data is greater than val. If that's true, then we pass in node dash m left. Otherwise, we pass in node dash m right.
So is it the same thing you just wrote up there?
Yeah.
Just.
So let's go ahead and test it just to make sure. Val mroot. Because we're saying if m node is greater than val, then we pass in m node dash m left to contains. Otherwise, we'll pass in node dash m right. Hey, look, it did the same thing.
I like it.
Hmm?
So I don't like that.
You don't like this?
Mm-hmm.
Well, you're gonna.
It's different.
It's different. You ever did the ternary operator? I never did ternary operator. Maybe.
Yeah, I don't know.
I think we have.
So you test this condition, and if it's true, you do this condition. Otherwise, you do that one. Or I'm sorry, this expression. Otherwise, you do that expression. All right. Well, that was search. That was fun. What's the runtime complexity of search?
In log event.
Man, we're just taking guesses here.
Or just log event.
Log event.
Log event. Why is it just log event?
Because you divide
Because
by
you keep
n.
dividing.
Yeah, divide by true. So on average, it's log event.
We know what we're talking about. Sort of.
We gotta speak
we
it.
know if
We
divide
got
it
to
in half,
enunciate
Then we
correctly.
thought about it.
We knew there were some logs in here.
That was the first show I've ever spawned.
So when you cut in half, it's like you're cutting a log in
I
half. Does that
thought
help any?
about it.
Exactly.
You're
Okay.
supposed to do that from the beginning.
Thinking takes work.
You should
All
just
right.
think that.
Let's. All right. So insert.
Caffeine has a
So actually, we've already done insert, which is put, and we've already talked about that. So, and we already did, yeah, we did it last time. That's
Yeah, we already did it.
with put, remember? Good old put.
So
So copy
same
pasta.
thing.
Yeah, here's put. Wow, we did it recursively pretty easily.
Why do we need copy pasta if you just rename it into?
And then, oh, we did put. Never mind. This is the real function up here. We determine if it needs to go, yeah, sign, put it on the left, otherwise you put it to the right. All right, and just traverse down. Woohoo! Okay.
Yeah. Same thing as before. We just called it put.
All right, guys. Here we go. How about delete?
Oh no. That's bad.
Delete is bad? Well, let's look.
Wait. How do we do it? Are we gonna search? Are we gonna do where we just like call search to find the value and then we say delete that value, place it with null or something, or what?
But then
Yeah, how do we do delete?
That's what I was
That's
asking.
exactly what that's how I'd imagine we do
Let
it.
them know that you
Yeah,
want to
but then
delete,
you
which
have
means
a
searching
null in
through
one
it,
of those
and then
branches.
deleting the
and then
node
it's just
itself,
like a flooding
but
branch.
getting the leaves of the nodes, if there are any,
Well, I
pointing
said
to
no, because I
the original parent of the deleted node.
Okay. Well, hold on. What would be the easiest node to delete in this tree?
Negative
And
one.
-1.
Why?
One at the bottom.
Because all you'd have to do is just get rid of it.
So you
wouldn't
just
have to change
erase it.
any point.
All right, that's good. How about the 1? What would we do?
We would have to.
You'd have to make
delete it.
2 point in the -1 and then delete the 1.
Right, so you just have 2 go over here. Basically, you shift this guy up. Okay. How about, what if, yeah, we don't have an example.
65.
We don't have another example of the opposite. Let's see.
Of the 13.
All right, let's add a number right here.
Oh.
Whoa, that's red.
Whoa.
Whoa.
Whoa. Smart.
Whoa. Okay.
Woo.
Said this. You can't switch colors on us in the middle of that diagram.
Yeah, that would just, the world explodes.
Yeah. It would ruin everything.
All right, so if we wanted to delete 23, what would we do?
You'd have to.
It's actually not that hard.
You just have to get rid of it and move everything up.
Yeah, so if you get rid of the 23, you just move this section up, so you have 56 point to 34, and 23 disappears.
Huh.
Okay. All right. Let's say we wanted to get rid of 56.
That sucks. 56 is right in the glare.
All right, so let's not choose 56. Let's say we want to get rid of 67.
When you just.
Wouldn't the 66 replace the 67?
Okay, that one was too easy. The 56 is the best one. All right, curse you, glare.
Just stand
There,
right
I'm going to
there.
stand right here. All right, enough of the shimmy. So this is the 56. What would we do to get rid of the 56? And we want the same algorithm to get rid of the 56 to have it work with the 67. There we go.
Just replace the 56 with the 63.
Okay, so how do you determine that? Just find the one to the right and shift it up? All right, would that work over here?
No.
No. Okay, so we need a better algorithm.
Wouldn't it be to the left?
Well, we do the left with the 66, that would okay here, but over here, oh yeah, that would work.
That would work.
That would
See?
work. But it wouldn't work if the 23 had a 15. There, making it super hard.
Why would that not work?
Well, if you put the 23 up here, the 23 would have to have 3 children. But this is a binary tree.
What do you mean that's for each other? Oh, if that, yeah, I'll get it.
This is a predicament.
This is quite the predicament. All right, first off, let me go to my code.
Rearrange the whole tree.
Rearrange the whole tree. Let me see if we. What do we need to fix up here? I think we need to add some things. Whee! Okay. What other values do we need to add here? We have the 7. Do we have the 34 or the 15? Do we have the 23? Okay, so we can add the 15, 34. What else do we have? The 30 and the 40. Let's make sure that didn't ruin anything. Looks good. All right. Well, let's go ahead and at least start. Well, wait a minute. Are we going to code delete, or is that for your exam? Not for your lab. Might be for your lab. Your exam, no, your lab. Oh, that would be fun for your exam.
No.
Ooh.
No.
We haven't been doing it enough.
Ooh. All right. We should probably code this up a bit. All right. So let's at least get delete started. What's the first thing we need to do?
Find where the
Find where
node is.
the node is. All right. So we'll go over here, back in public, contains. We'll go bool delete constant t at some value.
I didn't like that.
That's because I should use the word remove. There we go. All right, so what's the first thing we need to do? You said find the value. All right, which solution should we do for that?
Search.
Right, so you want me to copy, which code do you want me to copy over? Huh?
The search code that we have pulled up.
All right. All right, we'll have, instead of rover, we'll have to delete. Well, to delete does not equal null. Actually, as well, to delete does not equal null, and to delete m data does not equal val. Just keep going down. That way, when we're done, to delete should pop up, right?
Gotta change the other rows.
To delete. Okay. Or if you wanted to go really fancy, to delete equals to delete m data is greater than val, if that's the case. Then to delete dash m left, otherwise it's to delete dash m right.
I thought it was a colon.
Yeah, I did too.
It is a colon. Did I type something else?
You
Just
did a
have to
comma.
comma.
Oh, commas. And sometimes people like to space them out like this. So, just to make sure that this part's working correctly, we'll go ahead and have what we have, remove of val. We are at, let's see.
There's no indexes.
Yeah, there's no indexes, so I'll just say found, and we'll have equal to delete. There we go, and that should give us a giant number. All right, let's go ahead and put the code down here. We don't care about contains anymore. Boom. std cout ib tree dot remove of 23 equals ib tree dot remove of 23. And we'll go and put the backslash in. And I also want to make sure it's not, we're not messing with anything. 24. All right, let's see if that actually compiles. Hey. So found is a number, otherwise found is 0. So that's a common way to do it because, well actually, what does this look like right here?
Address.
That's a memory address. That means it actually has a node with that value. So it did find 23 in the binary tree, but did not find 24.
Because 24 is not a
Right, so it was null at that time.
Oh,
Yeah.
sounds right, yeah.
Yeah, so far we're doing well.
So we can delete that memory address.
Well, hold on. If we're returning a bool, so if to delete equals null, we want to go ahead and just return false, right? Otherwise, we're going to need to return true because it was found. Okay. Then we'll go ahead and recompile just to, there we go. Now it actually is going to put out numbers that make sense. Found is at this address. Remove, yes. Not found, so we're not removing. But of course, we actually haven't committed the remove yet, so we need to figure out how to do that first. Okay,
What was the 64 it was before?
the 64. What's 64?
No, when it was doing the, because right now it's doing the actual, like, true and false. So what was the 64?
That was just whatever value was at that location when it returned from the function. We didn't actually return something, so the behavior is what's the term?
Undefined.
Undefined, right.
I was going to say unexplainable, but...
No, it is 100% explainable, but it's officially undefined. What?
I said, but nobody has that much time.
Nobody's got time for that. Nobody. Nobody got time for that. Nobody's got time for that. That's right. I need to be able to play that at any moment. No one got time for that.
We just need to get you, like, a playlist.
Have a little keyboard right here. Ain't nobody got time.
occurs.
Ain't nobody.
Ain't nobody got time for that. Recovering passwords.
Oh, recovering bad. Yes, recovering passwords. All right. So if it's the 23, well, that's not. Ooh, that's gonna be tricky.
Tricky.
Let's try and delete something that's easier to delete, like the 15.
Or the -1.
Or no, we like negative numbers. It's the imaginary ones we're skeptical of. All right, so I found the 15. So, is the 15 easy to delete?
Yeah.
Yeah,
Why is the 15 easy to delete?
because it doesn't have any children.
It has no children.
Good.
It's a bachelor or a single. I'm sorry, no. That came out completely wrong. We're going to just ignore that for now.
That's on tape.
It's on tape. Yes, tape. Not. It's not being recorded. It's on tape.
Yep.
Whatever.
We'll have good giggles later.
All right. If that has no children, then what do we do?
Then just delete it.
Delete to delete. There we go. And are we done?
With that point,
We have one problem.
if it does have children.
Well, hold on. This code's not correct. Because technically, what this does is it deallocates the 15, but it leaves the pointer. Boom, boom, boom.
So we need to change the pointer to null.
Yes, so how do we do that?
Whatever one's before it's the M left or M.
All right, so we need to have a
Previous.
previous. All right, we'll call it, previous. Prev.
Ooh.
Why don't you just call it parent?
Thank you, Sydney. Parent.
Welcome.
So, we go down the line. If we, I forgot what I was doing. Oh, yes, we'll have the parent equal to 2 delete.
Free.
What? And then we'll have delete go on. That way, that can be found. Right. To delete. All right, good. Deletes 2 deletes null. Then we get out of there. If 2 delete, the 2 children are null. Then what do we need to do?
The children. Parent, wherever delete is.
Equals null.
Uh-oh. Which one? M left or M right?
It depends.
It depends.
I don't know.
All right. There's the hard way and the easy way.
Let's do the easy.
You sure? There's the easy way to code, the hard way to understand, and the easy way to understand, and the annoying way to code.
Super.
I don't know. It depends.
All right. So I'll have parent be a pointer to a pointer.
Ooh. Okay.
Okay.
I got it.
We're with you so far.
It's a pointer to a pointer.
All right. It's a pointer to a pointer.
Okay.
So now, oh, this is gonna be hideous.
Yay.
So, parent we don't want it to be equal to the actual data, but we want it to be equal to the pointer to where toDelete is going. All right. So parent, let me make sure that code's correct. Good. So parent is going to, I should comment this.
Yeah. I might be doing that.
All right, so parent will point to the
Previous.
pointer that is pointing. Oh, this is to delete.
Point to the pointer
Wow,
that's
this is.
pointing to this.
Parent will point to the pointer that's pointing to delete.
This is the easy one. Which one is it?
This is the easy way to code
Oh God.
because all you have to do here is go.
Oh.
Okay,
That's why it's easy to code
that makes sense.
because now you're just setting that pointer equal to null.
Yeah.
How? Okay.
Okay.
So it figures out if it's going to the left or the right.
Right, and then it saves. Then it points to whatever that pointer is, so later you can manipulate that pointer inside the binary tree.
I think I got it.
All right, good.
I was confident.
Maybe.
Maybe. All right, and then we'll return false, and we should also do delete. This is in the wrong
I was
place.
about to say.
Woo, that was bad. What are you doing? All right, so after the 15, we'll see if we can print it out, and the 15 disappears.
It
The-
does.
It
Yeah.
disappeared.
Woo!
It worked.
It worked. Now let's not do the parent equal to null, and let's see what happens. Hey, it was 0 that time. The 0 popped out of nowhere. Huh.
Yeah, they didn't do 0.
Why is that?
Because it's still.
We deleted it, which means its behavior is.
No.
False.
0.
False. One of the two. I can't remember which
We deleted it, so now that pointer is pointing to something that's been deallocated. Therefore, its behavior is
No.
No.
undefined.
Undefined.
It might be null. It might be something else. It could be anything. We don't know. It depends. That's right. It depends. So set
It depends.
parent pointer to null. Parent pointer to null to delete the previous pointer. Yeah, that was a lot of text. Great. All right, so that was case 1, and we'll just return true if toDelete has no children. All right,
Has not children.
has not children. It never had children.
toDelete has not children.
Has not children.
You have not children.
All right, what would be an easier one? So what if we wanted to, after we deleted the 15, we wanted to delete
How about the 1?
the 20? All right, we'll delete the 1.
Because it has one child.
It has one child.
One million.
Namely, yeah, it has one child. So let's go down here. Let's set up deleting the 1.
Deleting one child.
No, just 1. Oops, that was the wrong button.
Oh, where'd you go?
I went to the end and then back to the top.
Wrong.
True. All right. So now if toDelete has one child, so in order to test that, we need to go toDelete and left equals null, or I don't know why I put a space there, but I did.
Wait, would it be does not equal?
Yeah.
If M left does not equal?
Yes, you
or-
are correct. Or toDelete dash M right equals does
Why
not
did it
equal.
say both didn't equal?
Then we have the one up top.
Right, so that's why I was double equal and I was actually correct. Because if they are both equal to, we would have gone through this code. Otherwise, we're just saying only one, if. Otherwise, we're saying if one of them is null, then we want to continue on. So up here,
yeah.
if
Okay.
both of them are there, we go into this code. Notice it's returning.
Yeah.
Otherwise, we're saying if you actually have one child, then we're going to jump into this piece of code.
Okay.
Okay? So if it has one child, what do we do? Well, let's look at this. This is actually very simple if we think through it. If you're at this 1, can the -1 replace it?
Yeah.
Okay. If we were, let's see,
Nowhere else has.
the 63, we already deleted the 15. Can the 34 just replace it? If we deleted that 15, which we have already, can 34 go in replace of the 23?
Yes.
Yeah.
Okay, so, excuse me.
It just bumps it up.
Yeah, so you just have to bump it up. You don't have to rearrange. You just figure out which child it is, shift it in there, update the pointer, and then delete the old node, right?
Yeah.
Yes.
Yes, comma.
Yes. All right, so that was the, we have no idea what you're talking about.
No,
No.
I think I understand.
So if this 7 wasn't here,
Yeah.
and you were deleting the 2,
You can just shift
bump
up
it
the
up.
1.
yeah, you just shift the 1 up. Okay. If this 63 wasn't here and you're deleting the 56,
You can just shift up the 20.
shift the 23 up. All right. So it really doesn't matter what's down that subtree, as long as one of the children is null or does not exist. You just shift that guy up and we're done. Right?
Okay.
Again, over here, let's say the 66 doesn't exist. We delete the 67. What do we do?
Just bump it up.
Yeah, just bump the 69 up there, and it's legal, right? Okay. Okay. So first we need to, we'll do binary tree node, so T child. And that's where we need to figure out if 2 delete him left equals null. If the left is null, then the child should be 2 delete dash m right. Otherwise, we'll have a 2 delete dash m left. In other words, have child point to the single child. So child is going to be a pointer. It's going to point to whichever child that is. In other words, if left is null, then child should point to the right. But if m left is not null, then it should point to the left. So we're just getting a pointer to whatever it is. Okay? Then,
We're deleting the parent.
so hold on. Now, where should the parent point to? The child, right. So now to just skip over, we'll just have parent equals child. And then we'll go ahead and delete to delete, and then return true. We chose the easy way to code, the hard way to understand.
I think we got it. We're learning.
Yeah.
I
Thumbs
wouldn't have
caps on.
understood this last year.
Huh?
Put thumbs caps on.
And then we return. All right. Let's see if that actually makes some sense. Does it work? So we remove. Oh, we should probably print it afterwards. Let's print after each time. Remove the 1, then remove the 23. Let's see if we lost anything. So did the 1 just get removed? Yeah. Then just the 23 get removed? Yeah. All right. Because the reason why we could remove the 23 is we deleted the 15 first. So we delete 15, 1, 23. So we get rid of the 15. That was easy. We get rid of the 1, moving the -1 up here. Then we remove the 23, which bumps the 34 up here. So all those could be done with the code we have so far. Okay. How's that?
No, it's fine.
That was fine?
Wonderful.
That was wonderful?
Now it's the fun one.
Now it's the fun one.
Yeah, the annoying one.
The annoying one. All right.
No, it's fun. What are you talking about?
I agree completely. It is great. Let's do 56.
Good. I didn't like 56 anyway.
Yeah, terrible number. Was that 7 times 8 or something? Who cares?
Hey, Dr. West, what's
Eh,
your least favorite number?
I don't have a least favorite number, but I have some favorite numbers.
What's your favorite number?
I don't know. There's a lot of good numbers out there.
Zeros and ones?
Those are good. 30 is a nice number because it's the product of the first 3 primes. So that's a nice number.
How come 30 is normal?
Nice
Oh, wait, it is.
number.
It's a nice number. 27's pretty cool.
67.
69.
15.
I think that's my favorite.
I mean, you gotta go with the binaries as well, right? 2, 4, 8, 16, 32.
15 on the Magna Carta was signed, and that's the day of my birthday. So
I'm gonna get it. No.
But no one's picking any real numbers or
85.
rational
I
numbers.
like 1,372,422.
To be your bank account?
Yes.
That's what I thought.
I'd be thrilled if that's what my bank account.
All right, so doesn't remove the 24 because it doesn't exist, and now we need to remove the 56. Obviously, we haven't yet because we don't know how to do it. All right, so let's go up here, and wow, this remove function is huge.
Yay.
Is that bad?
Now remove, it could be. Now remove a node that has 2 children.
Dot, dot, dot. And then he hummed it.
And then I'm it. Yeah, you know what that means.
Yeah. Man.
No problem.
All right, we're trying to remove this 56. Remove the, well, actually, let's just leave it like this. That's perfectly fine. If this was the 56 was the first number to be removed, just like this, what should replace it?
That's 23. No.
No, can't be a 23.
The 63?
63, okay. But if we were over here in the 67, which one would it be?
It'd be 66.
Okay. Can anyone see the property that both 63 and 66 have?
They're both divisible by 3.
They're both what?
I almost said that.
Divisible by
We need to find a node that's divisible by 3.
I thought about it. I was like, nah.
So, good guess.
They're children?
No, they're children, yes. So they have to be children of the node. And
They have nothing after them.
Yeah.
nothing after that. Ooh, okay. So that last bit was most important, but they can't be the immediate children because we could have something like this. Now I gotta write more. I gotta add to our binary tree because of
That ain't our fault.
Trees do grow over time.
they do grow until you chop them down, but that's okay. And then I guess we got to put
That's nice.
64 is the only number we can put in there. So let's go ahead and add that to our binary tree real quick in our code. Yeah, I know. Y'all are making my life difficult.
Make it
You
your
let
life
us pick.
difficult.
You let us pick numbers.
That's true, I did. I'm starting to regret that decision. So 57
You
and...
said at the beginning this was going to end up being a lot of numbers.
Well, luckily I haven't had to draw a stack yet, which is good.
Aww.
All right, now, let me get my head in the way. Fat head, there we go. So now how do we get rid of that 56?
Just erase it. It's fine.
What number should replace that 56? There's 2 numbers that would make it easy. Let me fix one of them so it's clear.
64.
Yeah, why would the 64 be a good choice?
Because
The child. There's nothing after it.
So we want to choose a node that has no children. Is there always going to be a node with no children?
No.
Yes.
Wait, yeah.
Yes, there will always be a node with no children because you got to go down the binary tree. Eventually you're going to find a node with no children. Okay, so we wanted to have no children. So why would this 64... Actually, the 64 would be a terrible choice. I lied. Let me fix the number that you should have chosen instead.
57.
57. Why is 57 a good choice? One, it has no children.
Yeah, and it's less than the 63.
yeah.
And it's less than every other node on this end.
Yeah.
So you don't have to shift them at all.
Right, so if you take this guy, bump him up here, then you're done, right?
Yes.
Right.
Okay.
Magic.
Magic! Okay. What's another node that actually has that characteristic as well? There's 2 nodes in here that do. That you could just swap them. 57, so it's the smallest of the large n, and the other one would be the
30.
30.
And the 40.
the 40. Only the 40. You can't just take the
Okay.
30 and put it up here because 34 and 40 are greater
Oh.
than it, so you can't do it. But the 40 being the largest of the small size, you can just flip it up to here because
So-
it's the largest, therefore everything over here will be smaller, everything over here is still greater
So you
because
look for the smallest of the
Big size.
big
Of the big
size,
size.
and then the largest of the small size.
well, hold on. You just need one of them, right?
Well, yeah, but you gotta look at
But
it.
if, yeah. Okay.
Well, you don't have to look at them, you can just choose, because obviously the smallest of the large sides can go here, and also the largest of the small sides can go up here, right? They both can go up there. So you just have to decide which one do you want. Which one do y'all want?
It might be simpler to do the small one on the big side.
The small one on the big side. So we have to find the smallest of the big side. All right.
When you just go to the left side has no children. Or the left side of the right side has no more children.
The left side of the right side has no children. Yeah, but I mean, this thing can just keep going, right?
Exactly.
Right. So you need to find the smallest of the right side or the largest of the small side.
Yeah.
Okay? I was just asking which one you wanted. You really just have to choose. It doesn't
I
really.
like the right side more.
You like what?
The right.
The right side? Okay. So how do we code this up? So we need to replace the node with the smallest node on the right side.
When you have to like loop through until you came to the end of the right side? Because that would be the
Yes, and I'm going to make this also slightly more complicated.
Dang it. He's yelling at us about making the tree too big, but he's the one who keeps adding stuff.
Oh. We have come up with these numbers.
All right, the 57 still needs to go up there.
Until there are no more lefts.
Right, so you go on the right side until you have no more lefts. Right. So we need to replace the node with the smallest node on the right side. So we need to go
Turn right to go left.
binary tree node. Oh, this is so terrible. All right. Smallest right equals, what was it? 2 delete dash m right. All right. All right. All right. All right. Okay. And then we're going to have while smallest right dash m left does not equal null, we'll have smallest right equals smallest right dash m left. Okay. So until it finds null, you have the smallest left. Great. Yeah. All right.
Things are happening.
Things are happening. So now we have that node. What do we need to do next?
Switch out that node with the node we're deleting.
Okay. So we can just do, first we want to have m parent equal to smallest right. So it points to that guy, right? So that would make this guy instead point to, whoop, I'm on the wrong side. This guy point to right here, okay?
Okay, and then you delete.
Hold. Oh, well, hold on. We don't want to do that yet because we want smallest right dash m left to be
Oh,
2 delete because we got to update all these pointers, right?
oh no,
Deb.
the left.
Teal.
The left
Do
is
lowercase l.
We're going to be okay.
No, it was an error.
Error. All right, so we update smallest right so that it's his new pointers. So now this
And now you
guy's
deleted it.
left points over here, and then his other one's pointing up here. All right.
Then you still you still
Don't you have to have it
59.
still
Something is
pointing to 59?
Oh yeah, we gotta fix this 59.
Oh no.
Oh no's! All right.
No.
Yes.
Aw, can't have three children.
So how did we do that last
Wait,
time?
So that's you do smallest right and left.
Let me give you a hint.
Pointer to it's M right.
Smallest right parent. So So remember that whole pointer thing?
Oh yeah.
You okay, Sydney?
Yeah.
You looked really sad when I did that for some reason. Smallest right parent equals smallest right. Okay, we need a reference there. So then before we update the right, we need to update the parent actually first. So we'll do smallest right parent equals smallest right dash m right. So whatever that is. So then what this line of code right here does is it makes this pointer instead point to this guy. I have so many arrows on this board, it's great. So the first parent goes to the 57, then the smallest right parent now goes to the 59. Then we're going to have the 57's left point to the 23. That's this line of code. And then we're going to have the 57's right point to the 63, that guy up there. And then we can
Delete the node.
delete the node.
Bye bye 56.
No one liked you anyways.
We win.
Okay, I feel like I should be commenting this somehow.
A little bit.
Huh?
A little bit.
Alright, first update the parent to point to the chosen node. Now update the chosen node's parent to point to the right. Because it can't point to the left because you don't have any children. We've gone down the left as far as we can.
Yep.
So we know that that's legal. Now update the chosen. By the way, chosen is smallest right. Right pointers to replace two deletes position in the tree. Wow. Now we can delete to delete. Now delete to delete and get out. Alright, I wonder if we coded this right.
Sure.
Almost. Oh, close. That's an easy fix. That is not the right line of code. How about 179? There we go. It needs to point, since it's a pointer to the pointer, we need to get a reference to that pointer, or a pointer to the pointer.
Yeah, you did a reference to the other one.
Alright, let's see. Yeah, segfault! Alright, what do we do wrong? I can't wait. Anyone?
Oh no, you defeated it.
Run!
Run, Forrest,
Run, Forrest, run. At binary tree 192. 192!
Right there.
2 delete dash m left. So if 2 delete. What? What?
Why do you not like it?
What is null? So this is that, val is that, and. Smallest right. Smallest. What?
Now you see why we have issues?
So 192? Yeah, come on. What's the problem?
That's a good question. What is the problem? I thought it was right. Apparently something is not.
Oh, hold on. Yes. What is the problem? No one's been looking. You haven't. No, wait, no, it's null, so it can't be null. Oh, that's not the problem. Well, let's go ahead and output smallest right and smallest left just to see what it is. Let's get out of that. Yep. Smallest right is 0. Why would smallest right be 0? Oh no.
Smallest right equals smallest right dash m.
So it starts with, let's put it up here first. I'll make it there. So smallest right does equal something and 2 delete does equal something else. That's good.
Until
And then, so the problem must be in here. So smallest right dash m left does not equal null. Update smallest right to the m left. And you keep repeating that. Oh, is it this guy? Because if the parent, no, it shouldn't be that. And then small.
it has to be inside the row, doesn't it?
Not necessarily. We might be having some fun pointer problems.
That would be possible.
No, it's
But
possible.
It's not changing smallest right though. Like the pointers used to be other ones aren't changing smallest right.
Oh, here we are.
Oh, that thing.
Yeah, that's not right. Because it needs to be pointing to the m left, not to smallest right itself. Make sure we are pointing to the actual pointer.
That worked.
There we go.
Huh.
Yay.
So it was just that.
Yep. Wow, that was, yeah. Oh yeah, because the pointer wasn't right. So did it get rid of the 56? It did! Okay. Now hold on. Let's make sure that it actually worked properly. Because we should add, what was it, a 59 afterwards. To test, to give us at least a little more confidence about what's going on. Alright, let's see if I just made my life harder. No, it worked. Alright. Well, that was fun.
Ta-da.
Any questions about delete? Everyone like delete?
Now that we understand it.
Sure.
Sure.
It depends.
It depends. I think I just did the lab for you.
That works. When, this one's due, is it due the Monday after break?
Yes.
Okay.
Alright, delete.
So the same day as our project?
Yes. And then I will sign your next project on that day as well.
I got a project.
Alright,
Sorry, what day did you do?
Monday.
Monday, so Monday.
Not spring break Monday, but the, when we come back Monday.
So we show Monday the first, so March 13th.
March what?
13th.
Yeah, that's
That sounds right.
That's also when the project is due?
Yes.
Okay?
If I haven't updated that, that's when it's actually due.
Okay.
So the delete operation has 4 cases. Hopefully you can see that. Let me update what's on the board so we're not looking at tons of squiggly lines that don't make too much sense.
Look at all the arrows. Oh no, you're deleting the arrows.
I am deleting arrows. That's what we do in class.
You see how easy it is for a human to do it? I mean, all you had to do was just kind of.
It's like bye bye.
Yes, but who's faster at it?
The process.
Well, actually, you
Dr.
have to
West.
take time to make the code and make it work. So
Yeah.
really, that is faster.
The professor's always faster when it comes to coding.
Precisely.
If the professor
Blind
doesn't
loyalty.
like it.
Blind loyalty. All right.
That's true, the professor.
So back to delete. It has 4 cases. If the node to be deleted is a leaf, what do we do? Okay, if we're deleting the -1,
You could just delete it.
delete. What else do we need to do?
Get rid
Delete the
of it.
pointer.
Don't delete the pointer, but have the pointer set to null.
Sure.
Get rid of that.
What is delete?
Now, if the delete has no left subtree or left or right subtree, so
That was the other thing.
what if we are deleting the? Wow, I really messed this all up, didn't I? Deleting the 1,
You just bump it up.
bump it up. And then what was the other example? I think we don't have it anymore.
Nope.
8 gallon. So if this 15 was
Wait, no, 57 has a right child.
okay, so if we delete the 57,
Bump it up.
bump it up. All right, and then what was case 4? Has non-empty left and right subtrees.
If it has children.
So if we want to get rid of the 56, what do we do?
Go all the
Smallest on the right, what's 57?
And switch it.
So you swap them. What order do you swap them?
Well, first you have to set all the pointers to the other things, and then you swap them.
Right, so we did the things with the stuff. No, okay,
Yeah.
hold on. So you got the
Yes.
57. That parent pointer needs to go to the 59.
Yes.
And then the
57.
13, the parent pointer of the what you're deleting needs to go to the 57. And then the 57's left needs to be the 56 left, and the 57 right needs to be the 56 right. And then you can delete the 56.
Yes.
Ta-da! Alright, now let's go look at it with pictures. After deleting the 45, you'll notice the 45 was over
I
here.
don't think that pictures are as good.
Okay, good. So remember, here's the 30. When you delete the 30, they just shifted the 35 up. So you see the 35 up there. And then what comes next? I think it's deleting the 80. 80. So if we were to delete the 80, what do we do? Hmm?
Bump it up.
Bump the 75 up to there. And that's how you can see the 75. If we were to delete the 50, which is over here, what would we do? Oh, they did the largest on the right. So notice that they went to the largest on the right, which was the 49.
Oh, largest on the left.
On the left, thank you. Largest on the left. So notice that they got that 48 up there, but they also updated so the 40 points to the 45.
Yep. We did the opposite of what you did.
Okay.
I think our way's better.
Okay. All right, here's the question. What is the runtime complexity of delete?
Oh.
Well, let's think about it. If we're just deleting
Well, you have to
this
start
node,
with one.
what is it?
In
You have to traverse the whole thing?
no.
No. So it's not in.
Log of n.
Log of n, because you just go down here and you delete it.
Yes.
Yeah.
Awesome. For deleting something that has one child, like the 1, what's the runtime complexity?
That'd be in log of n.
In log of n. Where are you getting this in from? Do you have to traverse the whole thing?
No. So
No,
it's
you-
just log of n.
It's just log of n. Again.
Okay.
You just have to update pointer.
I didn't know if you had to add an in for like deleting.
All right, here we go. Now take your time to think about this.
Log it.
Yeah, I know.
If you're deleting the 56, what's the runtime complexity?
Log
Log
in.
it.
Why?
Because all you're doing is deleting doesn't change it. It's the searching that's.
Yeah.
Right, so you go here, and then you have to find the smallest on the right. So that's just really one long login algorithm. You're just keeping track of 2 pointers, or some pointers in between.
Yes.
And then to update the pointers is O of 1. So log of n plus O of 1 is just log of n. So delete is actually log of n. A lot of log of n's.
Yeah.
Yes.
Why do you think it's so good for searching?
It's because it's log of n.
Way to go, Captain Obvious.
I'm just trying to help you out.
I mean, that's a pretty good answer.
All right, some analysis. Suppose we wanted, okay, blah, blah, blah.
Yeah, that's-
All right, first off, worst case behavior. If you binary tree turned into a linked list where,
Okay.
yeah, everything on the left was null, everything on the right was null. O of n key comparisons, aka sadness. Average case behavior. Well, if you do some of the
Oh no.
complexity, blah, 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 blah. Basically, it's still a log of n, although you can't guarantee that it will always be log of n.
Yeah, every once in a while it'll be in factorial.
And notice that that is for searching. Let's see. Average number of nodes visited, it's log of n. Number of key comparisons, again, log of n. All right, let's stop here for a moment.